The smell of fumed silica in the morning. Delicious. So I have the burnt half out. I have my hands all nice and dirty now. And I found out that every single one of the transistors on both sides is bad, as well as some of the control transistors over here. A lot of these resistors on both sides are bad on the other side of the board. Some of the capacitors are bad, and some of the diodes are bad, and some other components that are rather difficult to source the exact right ones, and I don't have the proper equipment to test if I do replace them. So is this repairable? Yes. The printed circuit board is in good shape. All I'd have to do is dismount things and clean it up, and most of the black would turn to nice shiny green, with a few burnt traces that are repairable, just like I did with the other half, but it's just not worth it. So what I'm going to do is pick this thing up, throw this in my garage so it quits stinking up my house, and reassemble the inverter with just the other half. This is inside the other half of the clamshell. This would be the top of the case, and those capacitors that were missing, they left black goo in each place for those capacitors. Where they were, they left black goo where each of them blew up, and they apparently sprayed out their electrolyte when they got too hot and boiled, and they're glycol based. It's like ethylene glycol, kind of like what you have in your car, but a very special formulation. Anyway, they left some of that goo behind on the top. I thought that was kind of interesting, but I can clean this up so it doesn't smell so bad anymore. And once it's all cleaned up, I should be able to put it together and have a pretty nice 3,000 or so watt inverter again. I'm just going to give up on making it the full 6,000. All cleaned up, inside and out. And there it is, the repaired 6,000 watt inverter. And yes, it is as massive as it looks. It takes up my entire table. It weighs about 35 pounds and it's just gigantic, which isn't necessarily good, but it does mean that there's plenty of thermal heat sinking. I made sure to properly put heatsink compound on the inner insert so that it heat sinks to this outer side quite well. And I ran it under load for a while, and this does warm up very nicely. Gets to be about the same temperature as that heatsink inside, so works better than when it was new that way, which I needed to do because the top part of the electronics are missing, meaning this only has 3,000 watts of boost. And I only put in half the FETs for the output stage 2, because it's kind of pointless to put them all in if I'm not running 6,000 watts. So this is a very nice 3,000 watt inverter. I did test it out. It ran multiple loads. It runs my air compressor, even with this entire bank of light bulbs running. I can power my dehumidifier and a circular saw and some other things all at once. It does quite a bit more than a typical 3,000 watt inverter does. Over here I have a peak power work zone inverter, 3,000 watts. And look at the size difference. Yeah, this thing's big. By the way, these are awful. Peak Work Zone 3000 watt power inverters. Don't get these, please. They're the same product as the Ames 3000 watt inverters. They're just rebranded, and Ames makes junk, so please don't get that. Anyway, so I do have one more thing that I'd like to do with this inverter, and I probably won't show it on camera because, yeah, it's kind of boring, but I want to see how efficient this inverter is now that I took half the guts out of it. And I'm just kind of curious on that because I know that this inverter, when it came out of the factory, was not very efficient. It's on the low end, really, for modified sine wave inverters, but it was a nice product in that it has pretty good load regulation, very low no load draw, and lots of other nice things. Pretty well built, decent quality inside, etc., etc. So I do like this inverter, but it's just not that efficient. So now that I have half of it removed, I'm kind of curious what that's going to do for efficiency. So I'm going to power it up and measure efficiency on it. And here's my test setup. I always like showing this so you know how I'm getting the results. This will be the last thing I do before I clean this table off and start the next project. But I have my multimeter connected up to the inverter to these top two leads. The top two leads are, they were intended for the top boost stage, and the two are just strapped together with some straps that can handle a couple hundred amps at the most. So from now on, I'll just use the bottom posts, which go to the actual inverter now. But these give me a convenient access point to measure the internal voltage, so that I'm not measuring the voltage drop of this connection here on my cables. And I have a couple of batteries over here. I won't have the charger running so that it's a more realistic voltage when I'm doing this test. And look what I have! Aha! An A&L fuse. 250 amps. It is a very cheap brand, and it shows. They just stamped out a piece of steel, put it in here, and called it a fuse. Now, really, I think this setup is more dangerous with the fuse than without it, but I'm just going to put it in here anyway. This fuse should not be located by the battery, because if there's a very high current and the battery outgasses, the fuse will open, it'll make a spark, and it could explode the battery. So I would be much safer off just leaving this battery shorted and having this inverter smoke until whatever inside the inverter opened up. That would be much safer, but I'm just going to leave the fuse in here for now. Also, because this is just stamped steel, it gets very, very hot before the fuse ever goes. Like hundreds of degrees Celsius before it opens, which is terrible. For one, it's going to overheat the battery over here and potentially weaken the joints inside the battery, which is extremely bad. That's how you get exploding batteries most of the time. Or it'll just corrode the connections because they're hot. Anyway, that's not what this video is about. So this is my test setup. On the output side, I have my kilowatt meter, which is pretty accurate, and I use it for all inverter efficiency testing. That way it gives me a very fair baseline. It's within a couple of percent anyway. And for loads, I'm just going to use resistive loads, a couple of heaters, and a bunch of light bulbs. So I will go do that and report what I find. I have my efficiency results, and they're about what I expected out of this unit, so I'm not disappointed because I already knew to be disappointed. But I could only go up to a little over a couple thousand watts or so because this fuse gets hot very quickly, starts crackling from the heat, and I don't really want it to blow open. And for that reason, maybe it's a good idea to not get the cheapest protection device you can find. Buying a safety device for $5 a 10-pack is probably a bad choice, and that's what I did here. It's probably a good idea to buy a more reputable brand. Anyway, I did get the data that I wanted, and I forgot to mention that I used a clamp meter on one of these cables to measure current, but I'll show you the results here. And here are the results, crudely drawn out. Under no load, it takes about 0.4, 0.5 amps. My meter itself takes 2 watts, so I didn't actually calculate the efficiency to be very low, but that's what it takes with the meter. And you can see in the right column there, with a 100 watt load, it's 76% efficient. And the efficiency peaks at around 1,000 watts at 86%. And then it starts falling again. And by the time you get to 2,500 watts or so, the output voltage is low enough that it's not very usable anymore. But that's not terribly atypical for a 3,000 watt inverter. So there's my PowerBright inverter. I didn't pay a lot for it, and I wasn't able to fully repair it. However, this inverter is by far the best 3,000 watt inverter that I have ever tested. Sure, it's not the most efficient, but it does power the heaviest loads by a long, long way. My previous favorite for a 3,000 watt inverter was an old Xantrex unit rebranded as MotoMaster. That one I modified so that I could run my air compressor. Well, this one needs no modification. It already can run the air compressor with about 1,000 watts in addition to it. So basically that means that it can do about 2,500 watts continuous, 3,000 watts for, I don't know, 20 minutes or something like that. And it has a very high surge. I didn't actually measure it, but it's high enough to start multiple power tools at the same time, even without this top board in it. In any case, I think I'll keep this one for my own uses, even though it's gigantic, but there it is, kind of repaired-ish. Thanks for watching.